Welcome to our journey into the endocrine system. Today, we are going to explore how your body communicates across vast distances without a single physical wire. Whether you are completely new to this topic or looking to deepen your understanding, we will build everything from the ground up. By the end of this session, you will understand not just what this system is, but exactly how it maintains the delicate balance that keeps you alive. To start, imagine you are in a massive mansion and need to send an urgent message to every room. You could run physical wires, which is exactly how your nervous system works. But alternatively, you could set up a powerful Wi-Fi router. The endocrine system is essentially your body's biological Wi-Fi network. Instead of radio waves, it uses tiny chemical messengers called hormones. These hormones are released into the bloodstream, washing over every single cell in your body, much like a Wi-Fi signal traveling invisibly through the air. Now that we have an intuitive picture, let us look at the formal biological definition. The endocrine system is defined as an integrated network of ductless glands. Unlike exocrine glands, such as sweat or salivary glands, which release their contents through physical tubes to the outside of the body, endocrine glands are completely ductless. They rely entirely on a rich, dense network of surrounding blood vessels to pick up their hormonal secretions. Once released into the bloodstream, these hormones travel systemically, meaning they circulate throughout your entire body to reach distant organs. Since these hormones are traveling systemically everywhere in your blood, you might wonder how they know exactly where to act. Just like a Wi-Fi network requires a specific password to connect, hormones only exert their biological effects on specific target cells. These target cells possess complementary receptor proteins on their surface or inside the cell. When a hormone binds to its specific matching receptor, it triggers a complex cascade of intracellular events. This highly specific interaction ultimately alters the target cell's function, gene expression, or metabolic rate to maintain internal balance. Let us visualize this process clearly. On the screen, you can see an endocrine gland on the left, made of a cluster of cells. Notice how it secretes tiny blue hormone molecules directly into the red blood vessel below it. The bloodstream carries these hormones to the right, where they exit and approach two different cells. The top cell is a target cell. It has specific Y-shaped receptors on its surface that perfectly match the blue hormones. The bottom cell lacks these receptors, so it ignores the signal completely. This perfectly illustrates target specificity. Understanding this targeted communication brings us to why the endocrine system is so crucial. It is the master regulator of homeostasis, ensuring your internal environment remains stable despite constant external changes. It governs virtually every long-term process, from your baseline metabolic rate to physical growth. For example, when you eat a heavy meal, your pancreas releases insulin to safely store the sudden spike in blood sugar. Without this rapid response, high sugar levels would literally poison your blood vessels and organs. When this system fails, it leads to widespread diseases like diabetes and hypothyroidism. Knowing how powerful these systemic signals are, we must consider what happens after the message is successfully delivered. A hormone's message cannot last forever in the body. If it did, the biological signal would never turn off, leading to absolute metabolic chaos. To prevent this, your body constantly filters and destroys these circulating hormones, primarily through the liver and kidneys. We can actually model this disappearance mathematically using the concept of exponential decay. This mathematical model allows us to predict exactly how much hormone remains active in the blood at any given moment. This brings us to the mathematical representation of hormone clearance. The formula is C of T equals C0 times e to the power of negative KT. Let us break this down conceptually. C of T is the concentration of the hormone at any given time t. C0 is the initial concentration, immediately after secretion. The constant e is the base of the natural logarithm. The variable k is the elimination rate constant, representing how quickly the liver and kidneys clear the hormone. Finally, t is the elapsed time. If the elimination rate k increases, the hormone disappears much faster. Let us see this formula in action with a concrete example. A patient's pancreas secretes insulin with an initial concentration of 100 picograms per milliliter. The elimination rate constant is 0.138 per minute. We want to find the concentration after exactly 5 minutes. We substitute our known values into the equation. Multiplying the rate and time in the exponent gives us negative 0.69. Evaluating the exponential part gives us approximately 0.501. Multiplying this by the initial concentration gives our final answer. In just 5 minutes, half the insulin has been cleared, which is crucial to prevent blood sugar from dropping dangerously low. That rapid drop in insulin perfectly introduces our next concept, biological half-life. The half-life is the exact amount of time it takes for a hormone's concentration to drop to exactly half of its starting value. There is a critical inverse relationship here. If the clearance rate is very high, the half-life becomes very short. This is why stress hormones like adrenaline have a half-life of just a few minutes, allowing you to calm down quickly after a scare, while thyroid hormones last for days to maintain a steady baseline metabolism. To calculate this precisely, we use a specialized formula derived directly from our exponential decay equation. The biological half-life, denoted as t sub 1/2, equals the natural logarithm of 2 divided by the elimination rate constant k. The numerator is a constant value of approximately 0.693. The denominator is the exact same elimination rate constant we discussed previously. This simple division allows us to instantly translate a continuous clearance rate into a practical, easy-to-understand timeframe. If the clearance rate increases, the half-life shrinks, meaning the hormone is destroyed much more rapidly. Let us apply this new formula to the thyroid hormone thyroxine. A researcher determines the elimination rate constant for thyroxine in a healthy adult is 0.10 per day. We need to calculate its biological half-life. We set up our equation by replacing the numerator with its standard numerical equivalent, 0.693. We substitute the given elimination rate of 0.10 into the denominator. Dividing these numbers gives us our final answer of 6.93 days. Practically, this means it takes nearly a full week for the body to clear just half of the circulating thyroid hormone. We have covered a lot of ground today, so let us review the key takeaways. First, the endocrine system acts as the body's wireless communication network, using hormones to send long-distance messages. Second, these chemical messengers only influence target cells that possess the correct matching receptors. Finally, the duration of any hormonal signal is strictly governed by its clearance rate and biological half-life. Mastering these concepts gives you the foundational lens needed to understand every specific gland and metabolic disease we will explore in the future. Great work today!